Morning, everyone. Today we have Basile Coron who will tell us about operatic structures in Matroid theory.
Right. Thank you very much for this opportunity to speak. So today in this talk, what I'd like to talk about is a possible connection between ideas coming from the theory of objects called operads and Matroid theory. And to put it simply, what we will show is that many algebraic invariants of Matroids, such as Chow rings or Orlik Solomon algebras, have global structures which are very similar to operads. Okay. And so even though in the end we won't be dealing with classical operads, I still think it's worthwhile spending a bit of time in order to understand what those are, because in the end this will be our main source of inspiration. And so this first part would be somewhat informal, but if you're interested in more details, I would recommend this excellent book called Algebraic Operads. And of course, I would also be happy to discuss details with you in case you're interested. Okay, so what is an operad and what does it come from? So I think maybe the first thing to say about operads is that they are a type of associative structure. So the keyword is really associative. And in a way, one could say that they are a natural extension of associative algebras. So let me just start by some recollections, some very quick recollections on associative algebras. So for associative algebras, we usually start with some vector space A. And we have some additional piece of information given by some morphism, which goes from A tensor A to A. That is a binary product. And of course, this binary product is required to satisfy the so-called associativity axiom. That is this identity. Okay. And this data, so the vector space together with this morphism, we call an associative algebra. And of course, when we have sort of prototypical examples of associative algebras, which are given by the so-called endomorphism algebras. And more precisely, whenever I have some vector space V, well, I can consider the vector space of endomorphisms of V together with the composition. And this, of course, is an associative algebra. And I think in a way, one could say that associative algebra are some sort of formal abstraction of this object. Okay, and when we have an associative algebra, a natural thing to consider are the so-called representations of that algebra. That is, we just consider morphisms of algebras going from algebra A mu to some endomorphism algebra or some vector space V. And what that does is it encodes an additional structure on V. So let's look at a very simple example. So let's say my algebra is just the following one. So I have the K is my ground field, and I just have one generator, let's call it delta, and I quotient by delta squared. Okay. And in that case, well, what are the representations of A? Well, so looking at those morphisms of algebra, and of course, by the universal property of the subject, this is equivalent to the data of some operator on V, which of course is required to satisfy the equation that this squares to 0. And this sort of thing, usually we can call that a differential structure on V. So in a way, we could say that this particular associative algebra encodes differential structures, right? And I mean, this is a very simple example, but I'm sure we can all imagine what else we could encode if we had maybe more generators, more complicated relations, then we would just get more operators on V, satisfying the same relations, of course. And that's very interesting, but at the same time, sometimes we are faced with vector spaces which have additional structure given by morphisms. But sometimes, of course, those morphisms can take more than one input. Okay? So for instance, an associative algebra is a vector space together with a morphism which takes now two inputs instead of one. So of course, we won't be able to encode associative algebras using associative algebras here. We run into some kind of problem.
So what is V in this example?
V is some vector space.
But
you mean this one?
the second.
There is no V, so those are both deltas. That was the problem.
But you're telling us all the maps from A to some n-morphism of some vector space V is the collection of differential structures on V?
Yes, exactly, because so a map of algebra from A to V is entirely defined by the image of this element. So this gives me this operator, and it should satisfy the equation that delta squares to 0. So
for every V.
Oh, okay. Any.
yeah, so this is any V. I mean, this is what you were.
Yeah.
For any V, this
Okay.
is this. Yeah. Okay, so we have this sort of a problem with associative algebras, but let's say we want to play the same game as with differential structure. We would like to encode associative algebras in some sense. So this is our plan. And if you want to be a bit more precise, I would like some kind of identity like this. So I look at all, so again, for every vector space V, I consider the set of all associative algebra structure on V. And I want to be able to identify this set as the set of representation of some kind of object. So we don't really know what this object is for now, but let's say we hope that maybe a representation should be some kind of arrow between two things. And the thing on the right should be should have something to do with V. So here it was the morphism algebra of V. But for now, we're, let's say, a bit in the dark, and maybe even this arrow is maybe not so clear what we want to put there. Okay. So how would we go on about this? So maybe if we go back to this silly example, the actual structure, meaning the differential, is just obtained as the image of some sort of formal element on the left by this arrow, right? So if we want a binary product, well, maybe a first guess would be to just put home V squared V, right? That way we can imagine that, well, maybe whatever is here, we would have some sort of formal element, and the image of this element would give us our binary product. So that makes sense. But here we run into a problem, which is the fact that, and now if we look at the relation which is supposed to be satisfied by my binary product, well, this relation does not live in home V squared V, because it lives in home V cubed V, right? Because I composed the two things, so this has three inputs, right? So this is the main problem. And the sort of main idea behind operads is that to solve this problem, we will consider all possible number of inputs at once, right? So I will consider, instead of considering just home V squared V, I consider the set of all, the collection of all vector spaces for any number of input n, where this is indexed by every integer. So my question mark was really more like a collection of objects. And as in the case of associative algebras, this is not just objects because we have some additional structure which is given by the composition. But of course, we can also compose multilinear endomorphism, right? So I can plug in multilinear endomorphism. So I also have some composition. Let me denote it by circle. Okay. So let me be a bit more precise about what I mean by this circle. So to be a bit more precise, so let's call this thing just O of n. My notation for this. So if I have, let's say, a multilinear endomorphism which has n inputs, so something in O of n, and another multilinear endomorphism which has now, let's say, m input for some integer n, then I can compose f and g. But as it turns out, I have many ways of doing that because I can choose in which input of f I will plug in g, right? Okay, so now I also need to make an additional choice, which is this input in which I will plug g. So this is just some integers from 1 to n. And given those choices, I can cook up another multilinear endomorphism, which is just this one. So as I said, I will just plug in g in the ith inputs of f. And then for the rest, I use the same variables. And this, of course, gives me a well-defined multilinear endomorphism, which now takes m plus n minus 1 inputs. So this lives in O of m plus n minus 1. Okay. And usually in opera theory, we like to use trees to depict this. So here we could depict this as follows. So we have our multilinear endomorphism f, which has n inputs, and then we chose the input I, and we plug in the multilinear endomorphism g. So let's just depict this. Okay. So now let's sum up what we have exactly. So we have a collection of vector spaces O of n indexed by the integers. Let's say maybe strictly positive integers, which are, so those are vector spaces, of course. And then I have those composition maps. So they go from O of n tensor O of m to O of m plus n minus 1. And I have n choice of them. So usually we call it circle I, where this I runs over the choices of my inputs. Right. So I have as many morphism like this, where I runs over integers from 1 to n. And of course, well, I mean, we're just doing composition, right? So it should satisfy some kind of associativity relation, right? This is just composition. So instead of giving you complicated formulas, I will use my trees. So let's say I'm in a situation where I want to compose 3 multilinear endomorphisms. Okay, so they can have any number of inputs. And I also choose some particular input in which I want to put those above. So I want to do this composition, and a priori I have 2 ways of doing that. So I can first do this composition and then the other one. But of course, this should be also equal to being things the other way around. We first do the composition below. And then the composition above. Okay. So this is one condition which is certainly satisfied by our composition of endomorphisms. And there is another situation to take into account, which is if now I want to compose things in this fashion. So let's say I again want to compose three multilinear endomorphism, but I want to compose them in that way. So I plug in both the same thing, and I have also two choices of inputs. Well, once again, I can do two different things. I can first compose this way, then compose with the last one, and I can do things the other way around. And of course, this should be equal to the other way. Yeah. Do we have those two relations for any choices of multilinear endomorphism and choices of inputs? Okay. And this data, so the vector spaces together with maps having this form satisfying those associativity condition, we will call that an operad. Okay. It's really the vector spaces together with the maps. Okay. And to be a bit more precise, so there are in fact several different variants of operads, and you may want to add a bit more data. In particular, you may want to add, as part of the data, an additional symmetric action at each level. So you may want to add some symmetric action. So Sn should act on On, which really makes sense, because if we're trying to mimic this thing here, well, this does have a symmetric action, which is given by permuting the inputs, right? So it really makes sense, and you can do both things. So it leads to either symmetric operads or just operads. And of course, the action should also be required to satisfy some compatibility with the product. Yes.
So I don't quite understand the problem you're trying to solve. So did you fix V and then you want to
Yes.
somehow
But it will
describe all possible structures?
Yeah, fix V. Yeah, you can, I mean, but it should work for any V, but I fix V. And I look at the set of all associative structures on V. And I want to express this as the set of representations of some objects. Exactly the same way I was doing this for differential structures. I look at all differential structures on V, and I want to express that as a set of representations of some object. So what I'm trying to understand is what those objects should be, first of all. And what I'm telling you is that basically those objects should be operad. And now, of course, the next step is to understand exactly what operad we should put here in order to make all of this form. Okay. Other questions?
So the thing you wrote down, like the free operad on this hall.
No, this is not a free operad. This is the analog of this. So it's not a free thing. It's a particular operad which I can associate to any vector space.
What should we call it?
This thing, we call it the endomorphism operad. So it's usually denoted by like this curly. So yeah.
This is just an example that allowed us to make those more general.
Exactly. So we were trying to a bit the same way we saw that associative algebras are some sort of formal abstraction of this, but we did exactly the same thing, but with this collection of objects, right? To try to abstract this thing, and we just noticed that. Well, I mean, we just abstracted this to get.
Please. So on this example, these are essentially tensor networks.
Tensor networks. What is this?
Because well, this home is a tensor, and people also draw tensor networks, like putting a dot and legs out for a tensor and joining them, which is, I think, exactly the operation you're describing.
Maybe we can discuss it. I haven't heard about that.
Do you really need all this for just mu? Mu is just from 2, and yet you introduced all these ends. You actually need to.
Yeah, that's a fair question. So possibly, so I haven't seen it, but possibly maybe we just need V squared and also V cubed, because as we saw, we had this problem. But I mean, if we want a robust theory, I think it just makes sense to put every end, because I mean, we could want to encode other types of things, and maybe we have even more inputs and so on.
So when you write this O of n, this notation, do you mean exactly that, or do you mean something abstract?
Right, so in this case, I just use this notation to mean that, but then
Oh, that's.
I just this is abstract.
Okay.
So yeah, maybe this was a bit confusing. Now I have any collection of vector spaces which I name O of n together with this, and this I define this as being an operator. The same way an associative algebra is a vector space with additional distribution. Yeah.
So I hope this makes sense, but so like this associative relation over here, that seems to me like on the left-hand side, you have like circle 2, and on the right-hand side, you use circle 1. So like how can I think of that associative relation as one of these, or am I not supposed?
It's not one of these. So this relation will come from this particular operad, which I will use to encode my thing. The same way, this particular thing, this particular relation, is really encoded in this, right? So I'm just going to cook up some very particular operad, which encodes this, but then I can have any other operad which will encode other things, the same way we had for associative algebras. When you can have other more generators,
Okay,
some relations.
So are we supposed to think of this as associativity of multiplication?
This is associativity of composition of multilinear endomorphisms. This is what it's trying to model.
Oh, okay, thanks.
But there is, yeah, it's not the same associativity as this. Yeah, maybe this was the. Yeah,
So in principle, if they want to like parameterize Lie brackets on V or something, there's an operator for that.
You're spoiling my no, that works. But yeah, we'll get to that, and you can all encode all sort of stuff. We will be, yeah. That's it. Okay. Any other questions? Okay, so let's try to come up with this question mark. All right, we want to understand what operad we should put here. And really, if we go back to this sort of silly example, the key feature that we used about associative algebras is that we can define associative algebras by presentations, right? Here we took the free algebra generated by something, and then we quotiented by some ideal, okay? And then this gives us this, and then the universal property of free things and quotients is exactly this equality. So, and as it turns out, well, we can also define free operads generated by a generator. So let's try to think a little about that. So let's say I give you V some generators. So here V, I mean my generators in an operad, they could have a priori any number of inputs, right? So I should really think of it more like a collection of generators, also indexed by integers. Okay. Where Vn are the set of generators having n inputs, right? Okay, so this is my starting data, and now I want to define the free, so we call it T, the free operad generated by such a thing.
What is the set?
Vn, so it should be a vector space. But you can just it could also be just a set, and then you take the span of this if you want a vector space. Yeah. So yeah, let's say vector spaces. Okay. So I'm going to try to define the free operad. So this is what I mean by T. So we will see where the letter T. I'm trying to define the free operad generated by those generators. Okay. So let's try to think about what this should be. And so if we think about it, the free operad should contain every formal ways of composing my generators, right? Whenever I have some generator in Vn, one in Vm minus one, I should have some sort of formal product of those two in my free thing. This is what we do for the free associative algebra. We look at all possible tensors of elements, so those are all the formal products that we can deal, okay? And something which was hinted at maybe by those pictures is that the ways of composing elements in an operad are governed by rooted trees, right? So so here we really see rooted trees appearing by just iterating those maps, right? And reciprocally, if I give you a rooted tree, and at each vertex I choose some elements in my operad, well, I should be able to compose them in order to get a multilinear endomorphism, right? If we think about the endomorphism operad, you just think about if I give you some tree, as I said, any rooted tree, like whatever shape it has, and then I choose at each vertex a multilinear endomorphism, then I can compose them in order to get a multilinear endomorphism. Okay. And really, if I just want to use those sort of partial composition, those relations tell me that I can do it in any order I choose, right? For any edge, I can do this composition and then this composition. And the fact that we have those equations tells us that it doesn't really matter which order we choose. Okay. Okay, so all of this to say that this free operad should really be just the linear span of trees decorated by V. This is what stems from this analysis. So this should be rooted trees And what do I mean by rooted trees decorated? I mean I take a tree and at each vertex I choose some element on V, which has the right number of inputs, of course. And I look at the set of all of them, and this is my free operad. Okay.
So by V, you mean it will be an element of Vn or?
Yeah. So
n equal to the number of incoming edges? Or?
Exactly. Yeah. So let's look at some examples. So let's say I have some tree like this. So the first level has 3 inputs. This level has 2. This level has 2. Then whenever I pick some set of some generator which has 2 inputs there, and I choose another one which has 2 inputs and one which has 3 inputs, this should give me an element in my free operad generated by V, right? So let's say we have V1, V2, V3, and I assume that V1 belongs to V2, V2 belongs to V2, and V3 belongs to V3. This is going to be an element in this free operad. Okay. So one thing you might be wondering about is that for an operad you need more like a collection of objects, but this of course is indexed by the number of the total number of incoming edges, right? So to be a bit more precise, this should live in so we have 1, 2, 3, 4, 5 inputs. So this should live in the free operad at arity 5. So we can just index those trees by the number of inputs they have. Does that make sense?
Shouldn't there be like one outgoing edge down from?
Yeah. If I want to depict something, yeah, it's rooted trees, so yeah, we have the roots.
But why is there a V3 there? Because V1 and V2 I'm a little confused because there's these inputs already coming out of the circles labeled V1 and V2. So there's already 2 inputs, and why is the third thing there? I don't quite understand.
Well, this is going to take an input, right? So if you think about it in terms of multilinear endomorphism, so here you have a binary product, another binary product, and you plug it into the first coordinate of this one, here in the third coordinate of this one. So let's do this just assuming that those are multilinear endomorphism. So what this tree means is that I'm doing V3. So V3 has 3 inputs, and for the first one I plug in V1. So V1 has 2 inputs. Then for the second coordinate, I just plug in those things. So I mean, it's just a free coordinate, let's say, three inputs. And then in the third input, I plug in V2. Okay. All right. So this gives me a well-defined multilinear endomorphism, which takes 1, 2, 3, 4, 5 inputs, right? So if you think about it in terms of multilinear endomorphism, this should really live in form of V. Okay. But yeah, we're trying to do things really in a formal way. And really, our space is just formally, we have a basis given by rooted trees separated by. That makes sense.
Yeah. It's multilinear, so you told us like a V2 tensor, V2 tensor, V3 inside T5. Something.
You could add also V1 again. Yeah.
Sure.
Yeah.
I guess I take linear combinations of these, and then there's multilinear.
Yes, yeah. You also have coefficients for every just. Yeah. It's really the. But I mean, if V is a vector space, then I guess it's already vector space. Oh, I guess you do need to take some. Yeah. So yeah, that's just.
Is there a V of 0?
That's a great question. So again, so there are many variants of operads. And so here in my variant, I wasn't allowing this, but you can actually allow this. And what it will encode, it will help you encode what we would call units, right? Because here, I mean, if I can put n equals 0, this would make sense. It would give me home of KV, right? And home of KV is just choosing some particular element. And I mean, this would help me, for instance, if I wanted to encode associative algebras with a unit, I could encode that. Yeah, that's good. So it really depends on your particular class of operads you want to consider.
What about negative numbers? So you can have more inputs than outputs, and then you can kind of have upside down trees.
Yeah, that's a very good remark, and that's another type of structure which we call a properad. So that could help you encode. So here the combinatorics would be just the combinatorics of graphs. So you could have things with several inputs and several outputs, and you would encode that, you would compose them as so. And what you would see naturally appearing are graphs instead of trees. And this also, I mean, this makes sense in terms of multilinear endomorphism, because this would mimic this thing. But this is another object. This is called a properad, and it also has a very nice theory. But here we're restricting to operads. Okay. So we just have rooted trees. Okay, so we have our notion of a free operad. So that's great because that gets us closer to things like this, but we still need to do quotients by ideals. Okay, and here I'm not going to, to delve too much on this, but essentially, if let's say I pick some elements in some operad, I can consider the ideal generated by those elements. What would that be? That would be any elements which I can get by composing my element with any other element in my operad. Right? I mean, this just follows the same pattern as you would do for associative algebra. You would take pure element, you multiply them by any other element, and this is how you define the ideal generated by those elements. And you can do essentially the same thing with operads. And then you can also quotient operads by ideal, which just means that you quotient at every arity by the ideal. So let me just give you the answer, the exact answer here. Okay. So I'm just going to put the three operads generated by one generator which has two inputs. So let me just denote it by V, this thing. So this is just a symbol, or rather if you want maybe K, this, if you want vector space. So it will be generated by one binary product. And then I will quotient by the ideal generated by the following thing. Okay. So this is an element in the free opera generated by this because it's really a tree indexed by, well, I only have one generator, so I can only index it by one index, decorated by this symbol. Okay. So this really lives inside the free opera generated by this, and this has a RT3, it has 3 inputs. Okay. And I take the ID generated by this, and I quotient. Yeah. So whatever that means, or maybe I was a bit too quick about this, but yeah, my plan was to move on a little, but so let's say we have a well-defined thing like this. And then, well, if we've done our job correctly, meaning that the free thing and the quotient should satisfy the universal property, well, a morphism of operand like this should be exactly described by the image of this inside of this. So this is just the image of some element in home of v squared v. So this will exactly give me my mu. And then this element should satisfy this relation. But in terms of multilinear morphism, this is exactly this relation. Okay. So we have just solved our problem of encoding associative algebras. Okay. Yes.
Could you read for me what, so that's the free operad and what?
So this is the free operad generated by just one element, which I do not have. So maybe this is a bit confusing. So let me denote it by any letter you want, gamma, okay? It's just a symbol.
But it's a tree. It's like a.
Yeah, but maybe, yeah, this is a bit confusing. I don't need trees, like, I just need some symbols, and then what I'm putting here is
like your tree.
Gamma. I decorate my tree by gamma.
Yeah.
Does that make more sense, maybe? So there is a bit of treeception here.
But could you tell us how is it like? What's V3, V4, V?
It's just 0. I have no generator in hierarchy. I don't have any generator because here I don't have any other structure which I want to encode. If maybe I want to encode the other stuff where I have some mu prime which takes now 3 inputs, then I would be forced to add a generator here.
So V2 is one-dimensional and all other are empty.
Yes.
Okay, thanks.
Okay.
So when you say rooted tree, it's like embedded in the plane.
Okay, so that's also a very good remark. So if we just do this without this symmetric action, then it's going to be planar trees. And if you want to add symmetric action, you have some complications, and then you would be dealing with abstract trees without embedding. Yeah, very good. Okay. Okay, so let's try to encode other things. Okay. So let's try to, I'm just going to define, now that I can define operads by presentation, I can just have fun and define other things. So let's say, let's keep it simple. And so of course this T stands for trees, which we have here. So let's keep it simple. I'm going to again just have one binary generator. And then I will quotient by the following relation. So this time I will have 3 terms, which will be the following. Yes. Yeah, this makes sense. Again, I have just one generator, again in which has 2 inputs. So as in the other example, I put Vn was 0 for the other. And then I quotient by this element, which is an element of the free run. Okay. So what does this encode? So we will play the same game, but again by universal property. of our product. So what does this encode? In this direction, this is very easy to see what it encodes. It encodes some vector space, I mean, some binary product mu. Or let me actually put it to bracket. Vision. So it encodes some binary product which satisfies this relation. So what is this relation? So we just read the relation assuming we're just composing Michelin automorphisms. So this gives us the following. So the first, I mean, this would be x, y, z. So I do the bracket of x, y, z plus the bracket of x with the bracket of y, z plus the bracket of x, z, y is and this, as you can see, is just a Jacobi identity, right? So we're just encoding Lie algebras. Okay. So this particular operad, really we call it as. We encode the associative algebras, and here it encodes Lie algebra. So we call it Lie. When it's really defined by this presentation.
What about anti-symmetry?
Yeah, so again, so this is why this is rather a symmetric operad, because as you said, you need to encode also the fact that it's symmetric. So here, for a symmetric operad, you will actually need to also specify the symmetric action on our generators, and here you would specify as well that the action of S2 on this is trivial. You also use this relation. So to encode this, then you would this would encode this. Does that make sense?
It's my minus there, I guess.
Yeah. Sorry?
XY is minus Y, so is what you want.
Yeah, yeah. So I cheated a little on. So in fact, this would rather be a Lie algebra on a graded vector space concentrated in grading 1. So this would shift everything. So you may have noticed that this is not exactly the Jacobi identity. There is some sign going in. So I mean, yeah, it's really more like the suspension. Yeah.
You technically prefer to do it with the symmetric structure rather than just putting in a new relation, which is like 1, 2 equals 2, 1. Or 2 plus 2, 1.
I mean, this would be exactly the same thing, because how do you what is 2, 1? It's just S2, 1 acting on 1, 2. This is how I define it. So you may be wondering why we can now choose inputs, and this is because I act with S3 on this. Yeah, so also I choose a little, yeah, but this is the same thing.
Right, there is, because I guess the third tree is the same as the first tree in your relation, except for the label.
Yes, exactly. So it's really important that I'm able to commute the labels. So this is why I really need a symmetric operator as well. And those are really abstract trees and not planar trees as well. That's possible. This S?
So that S, you wrote S.
Our S stands for the suspension of it's the suspension of Lie, because as I said, it doesn't really encode Lie algebras, it encodes Lie algebras on the suspended vector space, which is now in grading 1. So I mean, you just put everything in grading 1, and this will change this will add some sign everywhere. And in particular, instead of having anti-symmetry, which you would have in principle for algebra, you now have symmetry because everything is in grading 1. But I mean, you can really just this is just a name for this. You can, and you will also have the true Lie operad. You would put 2, 1 equals minus this. Okay, so now we have all those examples. And let me give you other examples. So we've just seen this example of the suspension of E. And well, there is a sort of trivial example where I could put for O of n, I can just define it to be k, my ground field. Then for the morphisms, I just take the trivial morphism, which go from k tensor k to k, and have such a thing. And obviously, it will satisfy this relation. And this operad, we call it com. Yeah. So I just define it to be the projection of k indexed by integers together with the trivial morphisms. And why is it called com? Because obviously it will encode commutative operad. And why does it make sense for this to encode a commutative operad? Because the operad which encode, commutative algebras, the operad which encodes commutative algebras, basically in arity n, it should tell you how many ways you have of cooking up one element out of n elements using just your commutative bracket. But for a commutative binary product, you just have one way of doing that. You just take the product of your n elements. So this really makes sense to just have k there. But then you can also prove, but anyway, so we just define this like this. And then we have other examples. So also one thing which makes operads very diverse is that you can actually choose in which category your objects live. So until now, so we were dealing with vector spaces. So the objects were vector spaces. The morphisms are maps of vector spaces. That is linear maps. But really, if you look at the definition, we're not using anything about vector spaces. We're just using basically the fact that we have this tensor product of vector spaces. But really, we could do this for in any category where we have a reasonable notion of a product. And this we call the monoidal category. But if you've never heard of this, for instance, a nice example would be, for instance, topological spaces together with the Cartesian product. And this is another example of a monoidal category. And then I can just have operads in topological spaces. So I replace vector spaces by topological spaces. I replace maps by maps of topological spaces, which could be continuous maps, and so on and so on. Okay. So you can really do this in any, this is really a choice we make of the category in which everything lives. Okay. And speaking of topological spaces, there is a very famous operad in topological spaces, which is called the little disk operad. So it's denoted by LD2. So to define an operad, I need to tell you first the objects. I need objects indexed by integers. And at the integer n, I define this as the set of all configuration of n disjoint disk inside the unit disk. So really a point in this topological space is really n disjoint disks inside the unit disk, which are labeled from 1 to n. So just to do a small for instance, look at this configuration. I have those three disks and they are labeled from 1 to 3. So this is just an element, a point in the topological space LD2. Okay. So those are the spaces, and of course it has some natural topology. And now I need to tell you what are the morphisms. So I need to tell you if you give me configuration of n disk and a configuration of m disk, I need to cook up a configuration of n plus m minus 1 disk. And what I can do is just insert the second configuration into one disk of the other. Okay. So I'm just going to write this as insertion configuration. That makes sense for everyone. You want to what?
It's fun.
Sorry?
Okay, I have a question.
Do you want an
Maybe
example?
a silly question.
Yeah.
How does this differ from point configurations inside of a disk?
That's a very nice remark.
Oh, you can't show one and two the other.
That's a very nice remark. So it's I have to say is homotopy equivalent to configuration of point because I can just shrink this. But if I don't have this, if I just have points, I won't be able to insert things. So that's actually very good remark.
I see.
So 2 is like the dimension, so you can get any arbitrary dimension.
Absolutely, yeah. 2 stands for the dimension of my unit disk. So here it was 2, but I could do balls of dimension 3, 4. Okay. Does that make sense? Maybe you can. And let me give you yet another example. So this time it will be an operad in algebraic varieties. So once again, I need to tell you the spaces. The spaces are the following. At index n, I consider this algebraic variety. Okay. So those are the objects. And then what are the morphisms? So once again, I need to tell you how I can compose elements in this. But as we know, an element in this, it can be seen as a tree of bubbles with mark points. And what can I do with trees of bubbles? I can glue them along a point. Right? And this will exactly give me my gluing of bubble.
M is your n plus 1.
So the plus 1 actually stands for we choose a point which will be sort of the root of our tree. And then when we glue trees of P1, we insert the ice point in the root of the.
Is this almost the same as the previous example?
It's related, but it's not the same. Yeah. Not exactly. Yeah. The spaces are different. Okay, and then we have one last example which we will be interested in, which is also quite geometric, but it's not at the level of spaces. You need to take the homology. And I will take the homology of M0n plus 1. Okay. Then what are the morphisms? So M0n plus 1, as we know, is just the open stratum of this. And this is, the complement is a divisor with normal crossings. And in this situation, we have the so-called residue morphisms, which go from open strata to smaller open strata. And the strata of this are exactly product of smaller things. And this is basically what we were using, gluing bubbles. You can also use this as just inclusion of some stratum. Right? Because when I glue two trees, the strata are exactly determined by the shape of your tree. And so you can put as the composition just residue morphism, or rather duals of residue morphism.
How much is the trick these for mechanic 1?
That's a good point. So, if n 1 and 2, sure. So you can just take a point, I guess, or it's just empty for n. That's a good.
We have topological quantum field theories that can be realized using this analysis.
So I don't know much about that, but I think if I remember correctly, a topological quantum field theory are exactly given by representation of some particular operad. I think it's this one maybe, but I think it's exactly representations of this. But I don't know much about that. Okay, so we have all those examples. And here comes the main idea of this talk, which is that in all those examples, we will be able to see those operads as just a small fraction of a larger object, which won't be indexed now by integers, but which will be indexed by geometric lattices, okay? Or matrices if you prefer. Okay. And when I talked about the object, I really mean the whole structure of the operad, so the objects and the morphism. Okay. And so the inclusion of integer will just be the partition lattices, right? So we will be able to interpret those as just restriction of a bigger structure to partition lattices. Okay. So what do those things have to do with the partition lattice? They all have something to do with the partition lattice. So what about this one? So maybe this one is maybe the least clear one. So SLI encodes the algebras. And so SLI of n at arity n, as we said, it encodes, it tells you how many ways you have of bracketing n elements to get one element. And it's a well-known result that actually you have n-1 factorial ways of doing that. Okay. Your basis, you have a basis given by n-1 ways of bracketing things. n-1 factorial. And n-1 factorial has something to do with the partition lattices. It's the dimension of the top cohomology of the partition lattice. So in fact, what I'm telling you is that if I look at SLN, this is isomorphic to the top cohomology, or even the cohomology, because it's concentrated in that degree of this thing. And here I just gave you the equality of dimension, but it's more than that. It's an isomorphism of presentation, and representations.
Okay. You mean the number, the dimension is the number of elements in it? What does it mean?
So here I mean the cohomology of the order complex of this process.
Okay.
What's that? Also, what's a partition lattice?
Okay. The partition lattice is the intersection lattice of the grid arrangement. And more specifically, the points are given by partitions, and the order is given by refining partition. So this is what you would get if you intersect diagonals. It's given by telling you which coordinates should be equal to the other. And this is why it's the intersection lattice of the grid arrangement. Question. So it's also, if you prefer matrices, it's the graphical matrix associated with the grouping of. Okay, so now we have this one. Then for this one, I mean, it's a bit silly where if we want to extend this to arbitrary geometric lattices, we will just put K everywhere. And even the morphism, we will always put trivial morphisms. So we can easily extend this. Now, what does this have to do with the grid arrangement? Well, as Victoria said, this is homotopy equivalent to the configuration space, which is homotopy equivalent to, which is the grid arrangement complement. Then if we want to deal with geometric lattices, we pass to cohomology. And this gives us for the Orlik Solomon algebra of. Now, what about this one? This one, it's well known that this is isomorphic to the wonderful compactification of the nth grid arrangement with respect to the minimal being set. So when we pass to cohomology, once again, we get the Chow of phi n with respect to the minimal being set. And for this one, well, this is also isomorphic to the projectivized arrangement complement of the nth grid arrangement. When we pass, I mean, here it's already the homology, so it would be the projective Orlik Solomon algebra of So all of those things have to do with the partition lattice, and we are just going to extend this to any geometric lattice. And now I need to tell you a little bit about morphisms, right? The whole point of operads is that we have morphism relating the objects between them. And as I told you, the morphisms in an operad are governed by trees, right? If I give you a tree, then it gives me a way of composing things. And trees also have something to do with partial lattices because a chain in a partial lattice is a tree or a rooted tree. So basically the philosophy is that we redo everything by replacing integers by geometric lattices and replacing trees by chains in our geometric lattice. Okay. This is what. So you maybe take a break here or?
Yeah, we'll continue after 10-minute break.
Good.
Non-access skeleton.
Okay, we'll continue.
Okay, so we will do, as we said previously, we will introduce a new type of structure where our objects are indexed by geometric lattices and where we have morphism which resemble operads. So first of all, what I need to do is we have the same thing as we had for operads. We could choose our monoidal category in which all our objects will live. So I do stress. So let me denote by C some monoidal category. And I mean, if you're not super comfortable with this, you can just look in your head just vector spaces over some fields with the usual subproducts. And since I will be using geometric lattices a lot, let me just denote by G, L, and the set of all geometric lattices. And I don't really care for the singletons, so I also assume that they are not single. Okay, so here comes the main definition of the talk. I'm going to define a GL operad. So a GL operad. Let's call it O is, and so a GL operad in our monoidal category C is a collection of objects O of L, where L runs over any geometric lattice. So as advertised, this is really a collection indexed by geometric lattices. So those are objects in my monoidal category C. Where L runs over the set of all geometric lattices. Together with morphisms. So morphisms meaning morphisms in my monoidal category M. Morphisms of the following shape. So we will have one such morphism for every element G in some geometric lattice L. And it will go from O of the interval 0, G, tensor product with the interval G1, where 0 just means the minimum of my geometric lattice and 1 means the maximum geometric lattice. So it goes from this tensor product, which is an object in my monoidal category, and it goes to O of L. And I have one such morphism for every choice of G in L. Okay, for all G in L. And I also assume that G is not 0 or 1. L is a geometric lattice. Okay, so those are the objects plus the morphisms, and of course they should satisfy some associativity condition, right? For operads, we had this those things, those relations. So what are the relations? So such that now let me consider any two chain in some geometric lattice. So I can consider the following tensor product of three objects. So I can consider O of 0, G1, tensor product with O of G1, G2, tensor product with O of G2, 1. Okay, so this is a well-defined object in my geometric, in my monad category. And when I start with this, I can do a priori two things, because I can use mu G1 inside this geometric lattice in order to land in O of 0 G2, so product with O of G2, 1. So here it's really, so I have tensored with, this is mu G1 tensored with the identity, because here I haven't changed anything. Here I use mu G1 to land in here. And then finally, from this I can land into O of L by just using mu of G2. This lands in O of L. Maybe and I can do things the other way around, right? I can first use mu G2 inside this geometric lattice. So this lands in O of 0 G1 tensor product with O of G1, 1. So this arrow is identity tensored with mu G2. And finally, again, I can use mu G1 in order to land in here. Okay. And of course, the condition is that this would be a commutative square. Okay. So a GL operad, is a set of objects indexed by geometric lattices together with morphisms satisfying this condition. Yeah.
Can you tell me what you mean by this interval? Because like I can have objects in my lattice. Like essentially what you want is like above G and below G, right? But I can have elements in my lattice that are like neither compatible to G, right?
Yeah, so an interval in a geometric lattice is again a geometric lattice. This is a geometric lattice. So O of this is really well defined. It's I mean, I have just a collection of objects indexed by geometric lattices. So in particular, in this collection, I do have some objects denoted O of 0G.
Am I just forgetting the things that are incompatible with G here?
They get shown on the left-hand side.
I see, okay.
Do you need the fact that it's a geometric lattice for this community?
No, that's a very good remark. So for this definition, I don't need anything about things. All I need is a collection of posets, which should be stable under taking intervals if I want to make sense of this. And which should, of course, I mean, have a maximum and a minimum. So it should be bounded, but that's only for the definition. So this is my definition. And then we have all the examples which I mentioned before. All those examples. So if I take the collection K indexed by geometric lattices, this has an Operadic structure. If I take the cohomology of FL, this has an Operadic structure. The collection of Orlik Solomon algebras has a Operadic structure, or maybe I should rather say the dual of this, because if you remember this example of the configuration things, the operad is really those things, and when I take homology, I reverse all the arrows. So I need to take homology. So those are examples, and the Chow rings are examples too. And finally, the projective Orlik Solomon algebras also. Yeah. So in principle, I will need to tell you, I mean, this is only half of the structure. I would also need to tell you what are the morphisms. So this will come in due time. Just let me notice that here for this one, again, I can just take the trivial morphism, right? Because here, just take K tensor K tensor K. This will satisfy this relation. So for this, it's really clear what's the structure. And we will just copying the notation. Let's come. Okay, so those are my examples. Let me follow up with the following remark. So for this condition, I only used a two chain, right? But I could priori do things with any chain. So let's say I pick any chain in some geometric lattice L. I can consider the same tensor product which I did this here, but for any of my whole chain. So I have this tensor product. This is well defined. And I could play the same game as here. I could start doing all the small products I want in any order I want. Right? So I pick any two consecutive elements. I have a morphism which merges the two. And having this commutativity for three terms will imply that in fact it doesn't depend on the order for any n chains. Okay. So the bottom line is that we actually have a well-defined map going from here to O of L, which is just obtained as any composition and any order of composition of all the things from here to here. So in the case of G1, G2, this is just this morphism. Okay. So we have a well-defined. And those are exactly the analog of our trees in for the operatic stuff. As I told you, if I concentrate on geometry on partition lattices, chains will be trees, and this is exactly the composition along the tree given by this chain. Okay, so this is really this stems from the data of this thing. I get it for free.
I guess you want to ask.
Before you had two associativity conditions in your definition of an operad. Now you only have one.
Okay, that's also a very good remark. So that's because I cheated a little. So when I'm telling you that chains are trees, it's not. I mean, it's not exactly true because a chain is a bit more than a tree. It's a level tree. It's a level tree because I have an additional datum of the levels of my tree. So in fact, I'm not exactly dealing with operads. I'm dealing with what we call leveled operads. And when we have levels, we don't have those two things because we never have this thing. This does not exist because I would first need to choose some levels. This does not exist. So this is why we end up with only one condition. But there is, if we really want to deal with classical operads, there is a way to do that, which is even more complicated, which would be to consider a collection of objects which are not indexed by geometric lattices, but indexed by geometric lattices and binning sets. And now, if I restrict to partition lattices with minimal binning set, in that case, I really do get operads because, I mean, in that case, nested sets in the minimal binning set of the partition lattice is literally a tree. In that case, it's literally a tree, it's not level tree. And if we do this, you would have two kinds of relation, one which is governed by two chains and one which is governed by two nested anti-chains. This is why we would get exactly an operad. Yeah.
Can you do a specific example?
Yeah, we will do
With
that.
the tree and the partition, like I just want to see this.
Okay. So I don't know. Let's look at. I mean, let's do something very simple. Pi3, for instance. Pi3. So what are the elements of Pi3? So I have this partition, and I have at the top I have this partition, and I have 1, 2, 3, 3, 4, and 1, 2, 3. So those are my partitions. And this, let's say this chain represents the following tree. Or rather, it's a level tree. This represents this. This represents 1, 3, 4. This represents 1, 3. Does that make sense? Those are okay. But I mean, yeah, I mean, we if we don't care about partial lattices, we can just forget about all this, just work on this for generic geometric lattices. Okay, so then I still need a little one more definition to get started. And this definition is again this question of finding free objects, right? We had this issue with operads. We wanted to define a free operad generated by something. And here I want to define a free GL operad generated by anything. And this is really important if I want to be able to encode things as we saw. So let me try to define a free operad. So first of all,
So can I ask about your example? So are these are unordered set partitions?
those are set partitions, yeah, set partitions which are ordered by refinement. As you can see, for instance, this one is above this one because this one refines this one.
But I thought in the tree, like you had an order on the vertices.
Like left to right order, you mean?
Sorry?
You mean like left to right order?
Oh, the left or right really doesn't matter. I just chose some particular. Yeah, this is what you meant. The left or
Yeah.
right. Oh no, I just chose this.
So like in the first tree, if you swap 1 and 2, that's the same tree, you're saying?
Yeah, it's an abstract tree. It's not a planar tree.
Okay. Oh, okay. Okay. Thanks.
So let's try to define a free operad generated by V. So first of all, what is it generated by? So in the example of operads, the set of generators, it could live in it could have any number of inputs. This is why we are generating by a collection of things indexed by n, right? Because we could have generators in every possible input. So here, the starting data is going to be also a collection indexed by n. Okay? So I start with a collection of objects in my monoidal category, which is indexed just some collection like this, which is also indexed by geometry. And also, I should say that in fact, if I want to define my my free object, so I should add a bit more assumption on my monoidal category. So in particular with topological spaces, it won't work as well. I need something a bit more algebraic. And just to keep it simple, let me just assume that C is just the category of vector spaces over some picture. Yeah. We will see exactly why we need this. Okay, so this is my starting data. This is my generator. And now I want to define the free operad generator by V. So let me create by F V or free. Is defined as follows. So what is an operad? First, I need to tell you what are the objects. For every geometric lattice, I need to give you an object in my monoidal category. And again, we did this for operads. The free object should contain any possible way of multiplying elements in V. Okay, so this led us to trees in the operatic world. But now our ways of composing, of multiplying elements are governed by chains in my geometric lattice. Okay, whenever I choose a chain in a geometric lattice, and in each interval I choose some element in my operad, I have a way of composing them. This is exactly this map in order to get something in here. So this means that the free operad generated by this at L should be the sum over all possible chains in L of V0 G1 tensor products to V GN. And those elements are really meant to you really should think of them as formal products of an element in here, an element in here, and an element in here. If I had an operad, I would really be able to compose them in order to get an element in L. But now it's really just purely formal. I just take this and I use this as some formal element, some formal composition.
Now, are you given the collection of V of L for every L to start off with? Is that part of the data to make F of V? Like F of V, I mean, V is what?
V of L is a collection of objects indexed by geometric lattice.
So starting off with that collection you made.
Yes, exactly. This is the starting data. So that, yeah. This is the starting data. And I'm defining the free operad generated by this. Okay, but this is only half of the structure. Now I need to tell you what are the morphisms, right? So I need morphisms like this. I need morphisms going from the free operad generated by V at an interval G, 0G, tensor product with the free operad generated by V at G1, for the free operad generated by V at N. This is the definition of an operad. This is part of the datum of an operad. I need to specify this in order to define an operad. Okay. So what will this morphism be? So, I mean, this is just a sum, I mean, we have summands indexed by chain. So I only need to define this, where this is an element in one of the tensor products, so indexed by some chain. And this is an element in a summand indexed by some chain. And here the chain, I mean, here it's a chain in 0G. So I have a chain in from 0 to G, and a chain from G to 1. And of course, what I can do is concatenate those chains, right? This will give me a chain in from 0 to 1 in L.
Sorry, I think I slightly got lost there. So for every geometric lattice, you choose some arbitrary object in your category, and that's your starting data?
Yes, exactly.
Okay.
And so essentially what I'm telling you here is that this is just going to be induced by concatenation of chains. Okay. Does that make sense? Yeah.
So the trees are supposed to model the associativity. Is there like an intuition behind this generalization?
No, trees are supposed to model ways of composing things in an operad.
Yeah. Why is this generalization from trees to chains a natural?
Sorry?
Why is this a natural generalization?
It's natural because of examples. I mean, so we had all those examples. just notice that they all have this very special structure. They all have those morphisms that things associative. Then we're just axiomatizing this structure and trying to treat them like in a very uniform way and be able to compare those Matroid invariants. That's the main. Okay, so we have defined the free operads generated by V, and this will help us define the notion of generators. So if you have an associative algebra, you can, and let's say you take a subspace of that algebra, you can ask if the elements generate your associative algebra. This just means that any element in A can be expressed as a sum of products of elements in B. But you can also define this more formally as the surjectivity of the map from T of B to A. Let me just, let's say I have some subspace A inside some A associative algebra. I mean, the definition of V generates A if the natural morphism from the free associative algebra generated by V to A is surjective. Okay. This is literally the definition. So I'm going to try to do that for my new object. I want to be able to say if I have a subcollection of objects in my operad, I want to be able to say if it generates the whole operad. So let me find the following thing. So I consider O GL operad. And then I consider V inside of O subcollection. So what that means exactly is just a collection of sub-objects inside. Inside the O of L for every. This is what I mean by this V in O. It's really a collection of objects inside O. Okay. And now I want to define V generating O. And this is as follows. We say that V generates O if the natural map going from the free opera generated by V at L subjects onto O of L. Okay. I'm literally just copying this definition. But this really, I mean, this is really what you would expect, right? So, I mean, what does it mean generate? So I want to say that any element in O can be expressed as a sum of products of element in V. And this is exactly what this tells you. Okay, so let's look at an example. Let's look at the simplest example we had, this commutative operad. So let me just recall what this is. So I define pom of L to be literally equal to our ground field K for every L. And the morphisms are trivial morphisms. So mu G going from com of rho G, so this is just K, also com of G1, this is just K. Those morphisms are the trivial morphisms. This is my definition of the operad com. And I want to find a set of generators of com. Okay, this is what I'm trying to solve. So first remark is that if you look at com of some geometric lattice of rank 1, well, this needs to be a generator because it cannot be expressed as a product of smaller things because there is no smaller thing. Like there is no operatic product which lands into a rank 1 because it doesn't have any elements in between. Okay, and the claim is that this actually generates the set of generators. So when I would pick just k in rank 1, this generates the whole of that. So I define V of L, a subcollection of L, to be equal to either k if the rank of L is 1 and 0 twice. And my claim is that V, this collection, generates common. And this is really not so hard to prove. So let's start by doing this a bit informally. So what generating means is that I can express any element in COM as a product of elements in my generators. But really, so I need to generate the element 1 in some geometric, at some geometric lattice n, let's say, or any n. But really, if I pick any maximal chain of elements in L, well, one is, of course, I mean, the products are really just trivial products. So one is the operatic product at this chain S of one tensor there are 1. But those elements are generators because I took a maximal chain, and therefore all the intervals are rank 1 interval, and therefore all those ones, so here one lives in form of 0G1, for instance. 0G1 is a rank 1 element, so this is just equal to V0G1. So I have successfully expressed 1 as the product of generators for every geometric lattice. So of course this means that this generates 1. And once again, if we go back to this remark that we didn't really need anything about geometric lattices, this would also hold for any posets because we're just using the existence of a maximal chain. So it's just maybe finiteness of your poset. So at this point, we still haven't used anything about geometric lattices. Okay, and then, and then if we look at the more formal definition, so what is the free operad generated by V at L? Well, I mean, V, it's just either K or 0 if the rank is 1 or 1. So here, if you can recall V of F of V, sorry, I sum over chains, but really this is going to be 0 as soon as one of the interval is not of rank 1. And if all the intervals are of rank 1, then it's just K tensor K tensor K. So this is just, so this is really just some vector space indexed by maximal chains of, with a basis indexed by maximal chains of. Okay. And then what is the map from F of V to of L to COM? This map is literally just sending a maximal chain to 1. So it sends S to 1. So obviously it will be surjective. This is our definition of generating. But now, the question. Of course, when we are dealing with associative algebras, we don't care just about generators. If we have generators, we're interested in the relations between generators. And essentially, that means that we're interested in the kernel of this map. But okay, so this map is exactly this map. So I'm interested in the kernel of this map. And if you think about it in terms of vector spaces, this is very stupid. This is just the vector space spanned by differences of chains. Right? So in terms of additive structure, it's really stupid. But really, I mean, if you think about it in an algebra, let's say you have some ideal in an algebra, you're not particularly interested in finding additive generators. You're interested in finding multiplicative generators. That is, you want to find a small collection of elements in your ideal which generates the whole ideal via multiplication by elements. Okay. So this is what we're interested in for this. So we're not really interested in having a linear basis. And in order to define all of this, I need to tell you what I mean by an ideal generated by something. Yeah. This is what we're trying to do. We want to express the kernel as the ideal generated by some small thing. So let me have the following definition. So let's say I have some sub-collection of some operad O. So again, by this, I really mean a collection of sub-objects indexed by O. I will define the ideal generated by V. So again, it should be, it's going to be again a sub-collection of O. So I need to define it for every N or every geometric lattice. And for every geometric lattice, our intuition is that it should contain every element, which is the product of an element in V and products an element of O. And this is what you would do for ideals in an algebra. You take elements of V, to multiply them by elements of O. So essentially, that means that we're looking at, let's say, the sum of over every G1 less than G2 in L of mu G1, G2, O of G1, tensor product with V, G1, G2, tensor product with O, G2. All right. This is what I mean by taking all the elements which I can produce by multiplying an element of V by elements of O. This is literally okay. Okay, so I have this definition, and now the question is to be able to express this kernel as the ideal generated by something. And the claim is as follows. The claim is that in fact this ideal is quadratically generated. What do I mean by quadratic? I mean that it's going to be generated by elements which are obtained as product of two elements. This is what I mean by quadratic. And if you look at it in this kernel, the only way we have an element, a quadratic element, are when L is of rank 2, because if it's of higher rank, I mean we have product of generators, and we have one generator for each element in the rank. So in a geometric lattice L, all the elements will have grading rank of L. So all of this to say that I define the following subcollection of the free opera generated by V. I define it as the set of quadratic relations of the kernel of f of V. So really this is the vector space spanned by elements of this form. Where H1, H2 are any elements in some lattice L. And this is only if the rank of L is 2. And then I take 0 otherwise. Those, as I said, are exactly the quadratic relations in the ideal, the kernel of this. Okay, and the claim is as follows. The claim is that the ideal generated by R at every L is the kernel of this map. So let me call it maybe phi of L. Yeah. So this is exactly what you would do for associative algebra. You find some geometric generators, and then you look at the kernel of the map from the free algebra to A, and this gives you your ideal. Then your algebra is just the quotient of the free algebra generated by the idea.
Here, are you electing G1 equals 0?
No.
You have to multiply in both the right and the left.
That's a very good one. So I should, with the convention that that of, I mean, I ignore this if G1 is equal to, yeah, that's a very good point. Because O of a singleton is not defined, but I really need to just say I ignore this. Yeah. Thank you. Okay, so let's try prove this. So as I explained to you earlier, this kernel is very simple. It's the linear span of RVL. It's the linear span of. So if we make this identification, it's the linear span of differences of maximal chains. So linear span of, let's say this is one maximal chain, and this is another one. This should be an element in here, okay? And now what is this? Well, it's every element which can be expressed as a generator, a product of generators, times an element like this. So in terms of chains, this is really just this minus this, because here we were in rank 2, times other generators. So in terms of chains, this is just differences of chains of the following form. So I start with the same chain, then I have some rank 2 interval, and I do the difference of this minus some other maximal chain in this same rank 2 interval. Yeah, so, and what I'm trying to prove is that those two spans are the same. Okay. So in other words, I'm trying to prove that if I pick any two maximal chain, I can find a sequence of chains so that every consecutive sequence are of this form. Okay. That's what I'm trying to prove, and this is true for geometric lattices, but not true, of course, in general for posets. Okay. This is actually the first point where we use geometricity. So for instance, if I was dealing with the following poset, obviously this would not be true because the difference of this chain and this chain, I mean, I won't be able to connect the two with only moves of this form. But for geometric lattices, it is true, and I'm just going to withdraw. It's not super hard to prove. So I have two maximal chains like this. And I'm trying to relate the two by moves like this. And what I'm going to do is just look at the first element of both chains. So let me call that G1, G1. And I can consider the join of those two elements. By geometricity, this is a rank 2 element. And then I can just consider any maximal chain which goes from here to here. And then by induction, I can relate those two chains. Then I have this move, which is of the form I like. Then by induction, I can relate those two chains. Okay. But it's not super hard, and we're really not using too much about geometric lattices. I mean, this would be true for things which have nothing to do with geometric lattices. I mean, it's just some very weird posets, and this would be true here. This doesn't have much to do with geometric lattices, but we still need to use some properties. Are there any questions?
Yes. I missed this. How do I read the right hand side?
This.
Yeah, what does that mean?
This is, so I have identified so the kernel of phi L lives in this vector space, which is spanned by max chains. And this is just differences of two max chains. So this is a max chain, S1 minus S2. Okay. And if you were dealing with associative algebras, so here you would have, I mean, here we have some quadratic algebra. And when you have quadratic algebra, a natural question is to ask about a notion called Koszulness. Is it Koszul? This just means we ask about, so we know that relations are quadratic, and then we keep going, we ask about relations between relations, and we ask if those are cubical, then we keep going, we ask about relations between relations, and so on and so on. And if this is true for every n, you say that your algebra is Koszul. And it turns out that we do have a notion of Koszulness for our new thing. And this will mostly follow from, we're just going to mimic the definition for associative algebras, because for associative algebras, you can define Koszulness using the bar construction of your associative algebra. And we also have a bar construction of GL operad. And we will ask the same thing if the cohomology of the bar construction is concentrated on the diagonal. So we just mimic the definition for associative algebras. And then by a simple computation, we can check that that com is Koszul. And this will come from the fact that the geometric lattices are Cohen-Macaulay, because the bar construction of com will exactly be the chain, the simplicial chain complex of the order complex of L. And the Koszulness of com will be exactly saying that the cohomology of this is concentrated in top degree, which is exactly the definition of Cohen-Macaulay. So com is Koszul because geometric lattices are. And really, if we were doing things with general posets, the Koszulness of com is literally equivalent to Cohen-Macaulay of all the posets. So I think my time is up, so I will stop here. Thank you.
Questions?
I have a question about the kind of ground structure that you use, and maybe it's two questions that may be related. So one question is, what are the advantages or disadvantages of working with geometric lattices as opposed to matrix, which of course are very close to each other?
Yeah.
And the second question is that, so I don't know if you've seen this work of Aguiar Mahajan by monoids on hyperplane arrangements, which seems somewhat related, and I think would speak to using oriented matrix here instead of matrix.
Yeah, that's a good question. So for the first one, why do we use geometric lattices in terms of matrix? The reason is that in fact, all the invariants that we use, they only see the underlying flat lattice of flats. So it doesn't add anything to deal with matrix. And in fact, those invariants are even zero as soon as there is a loop. So it really sees the flats in the geometric lattices, so it won't add anything. But I mean, of course, if you have some invariant that you like and which sees loops and stuff like that, then it would make sense to work with matrix instead of geometric lattices. And then for the definition, you would just replace interval 0, G1, G1, G1 by just the restriction and contraction of your matrix. It would be a valid definition. But personally, I don't know examples of that. Geometric lattices. And then for your question about oriented matrix, you can do all of this with oriented matrix. So you replace geometric lattices by oriented matrix, and you keep just the flat. And that's actually interesting. So you actually get more operads this way. So for instance, you can look at the operad of chambers of your matrix, and I mean this is an operad in the formalizing of oriented matrix. So you get more stuff if you consider oriented matrix. That's interesting to look at.
What about for arbitrary building sets?
Sorry?
Oh, for other building sets, that's not just the maximal.
Yeah, so there is You can have a more elaborated version of all of this by, instead of looking at things indexed by geometric lattices, you can index them by pairs of geometric lattice and maximal building set, and building sets. And this would just be the restriction to maximal building sets. And you can do this whole thing. And the idea is that now we will replace chains. So this is what we had here. We had chains which governs our things. We will replace chains by nested sets. And then we need to redo everything again with nested sets. And it's actually a bit more complicated. So for instance, an important thing about chains is that we can concatenate them. So something we use actually in the definition of the free operator. And the same thing is true for nested set, but it's less clear. You have to work a bit more with.
So this term, do you still have this term in that setting?
This one?
Yes.
Yes, this will work. I mean, so you mean in the setting with building sets?
Yes.
Yeah. So if we're doing with building sets, the bar construction of COM will not be just the simplicial chain complex of the order complex, but the simplicial chain complex of the nested set complex. And this is also known to be concentrated in the right degree, so this will work just as well.
So, I mean, this proof of the flips will work for Macaulay too, right?
Yes, that's a very good point because I mean, Koszul will imply quadratics, which will imply so basically it just proved that being Cohen-Macaulay will imply this flip thing. And I don't know if this is easy to do it otherwise,
but so when is it exactly that you see a better behavior for geometric lattices over Cohen-Macaulay posets? Because so far in this setup here, you could have done all things for Cohen-Macaulay.
For the operad common, everything was just as well for any Cohen-Macaulay thing. But then we have other operads. We have the operad of Chow rings, Orlik Solomon. And for those one, I mean, it's not even clear how you would find things for Cohen-Macaulay things. So I really think geometric lattices are sort of a sweet spot where we have a lot of examples which make it a lot more variable. I mean, this sort of series really thrives on examples, right? It's all the more interesting if you have more examples.
Can you briefly tell us some more examples that are Koszul?
Yeah, so actually all the examples I mentioned are Koszul. So for instance, what about Chow rings? Chow rings, the operad of Chow rings is Koszul. Let me just mention that this has nothing to do with the Koszulness of each ring, which is also true, but it has nothing to do with each other. And the reason it is Koszul is actually very geometric, because so if you look at the bar construction of CH, so I haven't really defined that for you, but actually it's just going to be the free operator generated by CH with some differential. And for instance, in the geometric setting, this is actually isomorphic to the first page of the spectral sequence associated to the inclusion of the projective arrangement complement inside the wonderful convertification. And by a result of Deligne, this first page converges at the second page. And of course, it converges. And Deligne also tells you that the cohomology is concentrated on the edge, which is exactly the definition of Koszulness, basically. So really, the Koszulness of CH is really about this result of Deligne, which has to do with mixed theory. But I mean, so this is the realizable case, and then for the in general, you have to work a bit more, and this has to do. So this is called isomorphic to this. This is what I told you about the convergence of this. This basically means that this opera is Koszul dual to CH, which is the definition. And this quasi-isomorphism was proved, for instance, by B.B. Denham and Fechner when they talk about Luray models for this. This is exactly it. It is also true. This is another example of a geometric statement which passes to the combinator.
This is true with arbitrary building sets,
Yes.
but the individual CH need not be causal in this generality.
Yes, that's correct. So all the Chowings of matrix, meaning when we take the maximal being set are causal, but it's not true for any being sets. In fact, if you take general being sets, it's not even quadratic here. And it's still open when it is created.
So the story of operads is something about like partition lattices and like intervals in the partition lattice. Are there other like classes of geometric lattices that you think have interest?
Yeah, there are, and also part of the motivation from all of this is to sort of unify. So people had noticed that we also had those kind of inductive structure, and they were dealing with other kinds of families of geometric classes, as you said. For instance, if you take just the Boolean matrices with maximal binary sets, I mean, just restrict this to Boolean matrices. This gives a well-known structure known as a permutate. But I mean, and you have all kinds of examples where you restrict to other families, and basically this thing just encapsulates all of them in one big structure.
People thought about like lattices of subspaces of a vector space over a finite field.
I haven't seen anyone doing this particular case. Do you think it would have particular properties?
I mean, people talk about like the Boolean lattice, the partition lattice, and this one too.
Okay.
That's 3 nice examples, that's all.
Yeah, so maybe that's an interesting idea.
Can you explain why this height true thing is important?
Oh, the height two. So basically, I look at height 2 because I want to prove that it's quadratic. And the height 2 is really the only place where I have quadratic elements, because if you look at L, which is of rank higher than 2, then those max chains, it will be, I mean, this identification is really identifying a maximal chain to the product of 1 and so on for the whole maximal chain. And as soon as you go above rank 2, well, you have something which is not quadratic because you have more than one element. But this is really the minimal thing we could do. I mean, those have to be also in the space of generating the element generating your ideal. So I'm just proving that this is quadratic. Okay. For example,
What about the intersection cohomology?
Yeah, so intersection cohomology of what?
Of this matrix varieties.
So yeah, so I thought a little about that. The problem is that it doesn't have, if you look at the structure of the strata of the intersection of the Schubert variety, it's not indexed by chains anymore, it's indexed by flats. And that means that you don't really have the same structure as you. So one thing, the reason why it works for Chow rings, for instance, is that the operatic structure on Chow rings is literally just the inclusion of the strata of your wonderful compactification in the radius bracket. And this works because strata are indexed by chains. And it's not true anymore for intersection for Schubert variety, so you wouldn't get an operatic structure.
There's one more.
Yeah.
Is there like a numerical? How would I guess that this is causal if I like look at some combinatorial numbers that come from these things? Does that have a consequence?
So yeah, so Koszulness actually implies some numerical implications Namely, it will tell you that some series is the inverse of the Koszul inverse of the Koszul dual. So it has some numerical implication, and the analog of this numerical implication is the following. So something I didn't mention is that another possible definition of Koszulness is via causal complexes. And when you use causal complexes, your definition of Koszulness is just saying that the causal complex is acyclic. So this would imply that its Euler characteristic is 0, and this would be your numerical implication. And so, for instance, what you get for the numerical implication that you get for COM. So first, you notice that the causal dual of COM is just the cohomology of the sets. This is because the causal dual is just the homology of the power constitution, which is the simplicial chain complex of the order complex. And in any case, but the causal dual of COM is just the homology of your sets. This is an operad, this is an operad. And what the acyclicity of the causal complex tells you is that the following sum, so a sum over all flats of L, the following sum. So if I were doing things with general operad, so let's say I have an operad O with causal dual O anti-Schwick. What the acyclicity of the causal complex tells you is that the Hilbert series of this operad of this times this and summed over G is 0. So what does it tell you for COM? It tells you that the sum over flats of the dimension of the causal dual, which is the homology, times the dimension of K, which is just 1. There is also some alternating sign. This tells the Koszulness tells you that this should be 0. But of course, this is well known because this is, if you look at it, this is just the recurrence property of the Mobius function of 0. Basically, with this, you recover that the dimension of this is the Mobius function of your this. Or you even recover the fact that the Mobius function is alternating and that the dimension should be minus something. So this would be the kind of numerical implication that you would get from Koszulness. And for instance, for OS bar CH, this gives you this identity that the reduced characteristic polynomial convoluted with the Chow polynomial is equal to 0, something which was noticed by Westphal.
Okay, let's save further questions for future discussions, and let's thank Basile again.